Now we're going to start a discussion on linear homogeneous differential equations. And this is an example of one. You've got a linear nth order differential equation, and it's got a zero over here. Okay, so you've got your second derivative here, your function value here, and then on the other side you just got a zero. In general, it looks like this. Okay, but what makes it homogeneous is the fact that you've got a zero over here, and you can contrast that with a non-homogeneous. Now these are both linear differential equations, but notice over here you've got a 12x instead of a 0, and the general form of that would look like this. So you got a homogeneous, non-homogeneous differential equation. We're going to focus on the homogeneous now. That's what we're beginning our discussion on. Now, I want to introduce you to some notation here at this point, although I'm not going to refer to this after this in this video very much. I just want you to be aware of this notation, and I'll use it a little bit. But we have these differential operators, the capital D. For example, if you look at this right here, this big D in front of 8 sine 2x, what that's asking you to do is take the derivative of 8 sine 2x. And what you will do is you're deriving this new function. Okay, so it transforms a differentiable function into another function. So it's transforming, this differential operator. We send a 8 sine 2x in there, and it spits out a 16 cosine 2x. It transforms into another function. Likewise, this d 3x to the fourth plus 7x, we just differentiate it part by part. And notice, you differentiate the first part, add that to the differentiation of the second part. So you're used to that. Now, just something to motivate how this notation goes. Think about this idea of dy dx. And what we're saying is that's just the same as dy, like that, capital dy. Now think about if I take a second derivative. Okay, so I've got d dx of dy dx. And of course, we're used to this notation right here. But using this differential operator, we've got the first derivative here, and then d on the outside, and it kind of lends itself to this notation. So that's the second derivative of y. Okay, so that's kind of a clever notation. And if you look at this differential equation right here, and we wanted to rewrite this using this differential operator, what we would do is we would say, okay, d with a little 2 up here of y, see? That's the second derivative of y, plus 5 times the first derivative of y right here, plus 6y equals 4x. And we could factor out the y, see, like that. Now, notice this part right here. This is also, we could call that whole thing a differential operator. And oftentimes we will do that. Notice there's no y in here. We factored out the y, and we just refer to this as L of y. So this part right here, this is a differential operator also, and we sometimes write that L of y. And this is called a second order differential operator. Okay. So we're just paying attention to this notation. So if we have a differential equation like this one right here, okay, just a standard linear differential equation, we can rewrite that in this way using our differential operator. Okay, and then you could factor out the y. See, like there, I factored out that y. And now we have this differential operator, L of y. And notice I'm just writing that without the y's. Okay. And that itself is a differential operator. Okay. And notice this whole thing, this whole differential equation can be represented this way. Okay. Now, one of the things I want to point out, remember differentiation, you can differentiate across pluses and minuses. So if you give this some thought, what you would see is that if you have L of alpha f of x plus beta of g of x, if you have L in front, you can differentiate across the plus signs. Okay. So in other words, this is the same as this. And I'll make reference to that in just a minute, but I'll utilize that in just a second. But that just goes with this notation. Okay, now I want to get back to the homogeneous equations. Let's suppose that we have this homogeneous equation right here, just a general one. And let's suppose that we know that y1 is a solution and y2 are solutions. They're both solutions. Now what that means is, if you put that in, if you plug that in here, what you'll get is a2 of y1 double prime plus a1 of y1 prime plus a naught of y. We know that equals 0. I mean, that's given to us. We're told that it's a solution. Now, we also know that y2 is a solution, so that tells us that a2 y2 double prime plus a1 y2 prime plus a naught y2 equals 0. Yeah, so both of those equal 0. We know this to be the case because we're given that. Now, let's put both of those in there. So let's look at this. Let's suppose we've got a2 of x, and we've got the second derivative. So we've got y1 plus y2, like that. Okay. And let me change the notation a little bit here. Let me do this. Let me do d2 y1 plus y2, like that. Okay. So I'm using that notation. Okay. Plus a1 of x, and here we go. Left off the d. Okay. So here's y1 plus y2. And then we've got a naught, y1 plus y2. So now, let's just see what that equals. Let me take out the 0. If you look at this, what you've got now is you've got a2x d2 y1. See, I'm clearing the parentheses here. I'm differentiating across. I'm differentiating this y1 and then this y2. So I've got, look what I've got now. And let me just clear the parentheses. I'm going to come back and finish clearing the parentheses, but let's see what we've got. I've got a1x dy1 plus a naught y1. Okay, so notice I just cleared and used the first term. This, and this, the y1. Now I'm going to go back and get the other part of this that I left off. a2x d, little 2 up here, y2 plus a1x dy2 plus a naught y2. Okay, now we already know that this part right here is 0. See, we found that up here. And we know that this part over here, that's 0 as well. So it looks like if we know y1 is a solution and y2 is a solution, then it looks like the sum of those solutions is also a solution. Yeah. And to state it a little more, a little more rigorously. Let's suppose that down here in the green, let's suppose that y1, y2, all the way up to yk, let's suppose they're solutions of the nth order homogeneous differential equation. Okay, so they're solutions of this thing right here, on an interval, on a particular interval. Then this is also a solution. The sum, you can multiply a constant by each of those solutions, add them together, and you still get a solution. Now, by the way, what we've got, and let me, I didn't use this, we could have done this proof using this notation up here. I ran out of room, but you can see it's the same thing. And that, I guess I can leave that to you to kind of make that connection, but this is the idea. And I showed it was true for a second order differential equation, but you can see how that this same argument would hold for an nth order differential equation. Now let's see how this works. Let's look at this this differential equation right here. This is an nth order, a second order differential equation, and we're saying that y1 is a solution. Let's see if it is. Let's see if I differentiate y1. Okay, so if I take the first derivative, I get 2e to the 2x. And if I take the second derivative, I get 4e to the 2x. And let's see if that's a solution. So I've got 4e to the 2x minus 4 times e to the, that's a solution. Look at that. I just plugged in there. Now let's try y2. Okay, y2 prime is equal to negative 2e to the negative 2x. Let's try the double prime. And I get 4e to the negative 2x. And now if I plug that in, 4e to the negative 2x minus 4 times e to the that's a solution as well. So they're both solutions. Now, if I use both of them, in other words, let's look at this. Let's suppose I've got y equals c1 e to the 2x plus c2 e to the negative 2x. And let's see if this works as a solution. And part of the reason I'm doing this example is so you'll see exactly what I'm talking about. We've got two solutions here. We've seen that both of them work. And now I'm going to find the derivative here. So the first derivative is 2c1 e to the 2x minus 2c2 e to the negative 2x. And here's my second derivative, which is 4c1 e to the 2x minus or plus 4c2 e to the negative 2x. Okay. Now what I'm going to do is I'm going to plug this back in. 4c1 e to the 2x plus 4c2 e to the negative 2x minus 4 times the original just putting in the original. Whoops. Actually, I started to put in the wrong thing. Okay, so it's, hang on. Okay, so it's c1 e to the 2x plus c2 e to the negative 2x. Okay, now let's see what that is. Now notice that this and this are going to be 0. And this are going to be 0. So, ooh, it works. Yeah. So that is called the superposition principle. So we'll be using that later.